Hello everyone, I am Jack Hughes, a senior in chemical engineering and the team lead for Project 23112, Solar Panels Over the Cap. Here's the rest of the team.
Hello, my name is Tyler Pearson and I'm majoring in chemical engineering.
Hello, my name is Spencer Babiak and I'm majoring in chemical engineering.
And my name is David Surjak, also a chemical engineering major. The objective of our project was to determine the method for evaluating how placing solar panels over the cap canals, which is short for Central Arizona Project, will suppress evaporation and offset the energy costs associated with moving water along the 336-mile canal. The goal of this was to develop a model that could be used to determine if these solar panels would be economically feasible. The Central Arizona Project is a 336-mile system that brings water from the Colorado River to southern Arizona. It runs from Lake Havasu to just south of Tucson. It's the state's single largest renewable water supply, and it serves more than 5 million people. The reason this project is worthwhile is because starting this year, parts of the Colorado River will be in a Tier 2 drought. This has caused Arizona's allotment of the river's water to be cut by 21%. The cap canals provide water directly from the Colorado River, and this accounts for nearly 40% of Arizona's water supply. The Central Arizona Project reports that about 4.5% of the annual water is lost due to evaporation and seepage, which is the goal of our solar panels to mitigate this loss. There are 15 pumping plants along the canal, and the costs were about $72.5 million in 2020, with our energy collection hoping to lower this value and make pumping easier. The USGS has flow rate data available for a 30-mile stretch from Lake Havasu to Boose Hills. We're going to use that 30-mile stretch as a reference for our estimations.
The main decision that needed to be made was the type of solar panel used. To aid in the decision of which solar panel was best for the project, a similar study put out by the U.S. Department of the Interior Bureau of Reclamation was used. This study examined a 975-foot stretch of the Cap Canal with a total energy generation of 1 megawatt. This study used thin-film solar panels with an angle of 33 degrees. However, farmers and canal users were surveyed, and they were not comfortable with thin-film solar panels being used due to the toxic materials present in these panels. Chemicals such as indium, arsenic, and cadmium would leak into the water if a solar panel were to fall into the canal, polluting the water. To avoid this, monocrystalline solar panels will be used. The Bisbee prototype, led by Ben and Caleb, helped further advance our project. The goal of the prototype is to determine the effect that solar covers have on evaporation. To compare results, we switched the angle of the solar panels to match the 5 degrees used in the prototype. The Bisbee prototype considers both north-south and east-west configurations. For the north-south configuration, there is 7 feet of space between the end of one unit of panels and the start of the next unit, and for the east-west configuration, there is only 1 foot of space in between. Our project will incorporate 6 feet of space in between to incorporate both configurations into our calculations. This is the PFD for our project. The dimension of the representative segment of the canal is 975 feet by 94 feet, with 3 feet of space on the outside for installation of foundations. The monocrystalline solar panels used are 3.3 feet by 5.5 feet. To cover the canal, one unit consists of 162 solar panels, and with 27 units, the total amount of solar panels needed is 4,374. The energy collected from the solar panels is then fed into 128 inverters to convert the 1 megawatt of energy into usable energy that is then sold to a utility station. For the 975-foot stretch of canal, the total cost of the project will be about $3.2 million. In addition to the cost of solar panels and inverters, the budget also includes the cost for electrical equipment, installation labor, the foundations, and the steel truss system.
There are 2 main components to consider when calculating the monthly evaporation rate of the cap canal with and without solar covers. These components are the evaporative flux and surface area, which can be multiplied together to get an overall rate of evaporation. To determine the evaporative flux for each month, we use an energy balance on the surface of the water under the assumption that the water in the canal is at a uniform temperature. This energy balance consists of 4 main terms. R sub n is the net radiation at the surface, which can be broken down into solar radiation and long-wave radiation. H sub s is the heat exchange at the air-water surface, which is dependent on the temperature difference between the air and the water. Due to lack of temperature data, this difference is assumed to be 5 degrees Kelvin. Lambda is the latent heat of vaporization of the water, which is multiplied by the evaporative flux, the term we are solving for. And finally, delta Q is the amount of heat stored or lost by the layer. For our model, we assume this value to be negligible because the temperature change of the water would be minimal, and the temperature data for the cap water is unavailable. To account for the solar covers, a few adjustments need to be made to the energy balance to calculate a theoretical minimum for evaporation. First, both the solar radiation and the long-wave radiation from the air need to be multiplied by the coverage percentage. The coverage percentage in our case is 83%. Next, the long-wave radiation from the panels needs to be accounted for. This adjustment is made in the expression for L sub n and is shown by the last term in the equation. In In that term, F12 is the view factor, which is the fraction of radiation given off by the panel that reaches the water surface. Calculating the flow surface for each month proved to be a little difficult because the canal is trapezoidal, which causes the flow width to change with changes in flow height. Calculation of the flow height for each month was done using Manning's equation for flow and open channels. Knowing the discharge flow rate at the beginning of our 30-mile stretch allows us to calculate flow height, which in turn allows us to calculate the flow width and overall surface area of the stretch. The model we created was used to analyze the 30-mile stretch from Lake Havasu to Boos Hills. Using average discharge flow rates and weather conditions, the flow surface area and evaporative flux were calculated for each month, which led to the displayed upper and lower bounds of evaporation. Without the covers, the evaporative losses were found to be approximately 580 million gallons of water per year, and with the 83% covers, they are found to be approximately 287 million gallons per year. This equates to an annual water savings of 293 million gallons.
Energy collection was evaluated based on the initial 30-mile stretch of the canal. This portion of the calculations was created with adaptability and accuracy in mind. Using the two formulas listed, a new or different section of the canal can be evaluated quickly. The vital inputs are dependent on the length and location of the solar structure. Inputs required are sunlight hours, number of panels, and panel capacity. Using a basis sourced from the Wilmot Energy Center and TEP contract for the commercial sale price energy, we can estimate for the initial 30 miles, a total of 138.8 million kilowatts would be collected, which equates to a total of 5.2 million in solar profit per year. Using our model, we calculated that the 30-mile stretch of the canal lost 580 million gallons of water to evaporation annually. With the addition of the solar covers, we expect this number to be reduced by approximately 50%. This results in a water savings of 293 million gallons of water. While this is not a direct product of our system, we can evaluate the water savings as an offset to the initial capital cost. The quantity of water was determined to be worth $152,000 at a cost of $170 per acre foot. This water savings is approximately the amount of water required to irrigate 890 acres of farmland. Using the initial schematic for 975 feet, all economics can be scaled up to match the model over a 30-mile stretch. This results in a capital cost of $518 million for construction and yearly maintenance of $75,000. With cash inflow of $152,000 and $5.2 million for water savings and energy collection respectively, based on the average life expectancy of monocrystalline solar panels of 40 years, the net present value becomes negative $384 million, and the internal rate of return negative 11%. Both provide evidence of the infeasibility of this project. However, there is potential for the project to reach a break-even point. With changes in materials and energy costs ever evolving, if capital costs were reduced to $114 million or energy sales to increase to 17 cents per kilowatt hour, the project would break even over a 40-year period. In conclusion, we determined that it would not be economically worthwhile for the 30-mile stretch. In the future, additional flow rate data may allow us to examine shorter sections. Our model can be easily used to examine these shorter sections and determine the feasibility of those sections.
Finally, the group would love to give a big thank you to Dr. Saez, Ben Lepley, and Caleb Eubanks. The guidance they have provided this year has been priceless, and we would not have been able to finish this project without their help. Thank you.